So next we are going to discuss the explicit forms of the wave functions. When we solved the simple harmonic oscillator using the series method, we found that the wave functions, the energy eigenstates, were given by a factor of the Gaussian times a Hermite polynomial. So here we have solved the energy eigenvalue problem, but we still don't know what the explicit forms of the wave functions are. So to see what the wave functions are, we just have to observe that the lowest energy state, psi 0, which corresponds to the eigenvalue E0 equals to half h bar omega, this is annihilated by A. So this is 0. But then this is actually a first order differential equation. We can now express A in terms of x and p. And we know that in the position representation, p is a derivative operator. So this thing can be written as m omega by 2h bar square root, and then x minus I by m omega times h bar by I d by dx. So this is the momentum operator. This is basically p. Acting on psi 0 gives us 0. So this is a differential operator for psi. So if I introduce x0 to be given by x0 squared is h bar squared divided by m omega, then this differential equation can be written as x plus x0 squared d by dx acting on psi 0 of x giving us 0. So this can be solved very easily. So to solve this, what we need to do is that we write this as d psi 0 is equal to minus x by x0 squared times d of x. If we integrate this equation, then we get a log, and then if I take the antilog, we get a constant here multiplying e to the power minus x squared by 2x0 squared. Now I can normalize this, and if I normalize this, then that fixes the constant c, and we can choose that to be real, and that constant c becomes x0 square root of pi, so not pi 0, just pi, and the whole thing under square root, times e to the power minus x0 by 2x0. So this is the wave function of the ground state of the harmonic oscillator. So to get the higher energy state, say suppose psi n of x, what we need to do is that we need to apply the operator, the raising operator, say n times. And if you do n times and raising it and apply psi 0, and then there is some normalization constant, which is a bunch of d, and that'll depend on this value n, what these d's are. So if we do this, then we find that psi n of x is equal to, if we are careful about this normalization constant, we get 2 to the power n and factorial n square root of pi, and the whole thing under square root, and then 1 over x0 n plus half to the power, and times a differential operator, which is x minus x0 d by dx, acting n times on e to the power minus half x squared by x0 squared. So this gives us an expression to derive psi n. And if we use this and the expression for the Hermite polynomial, this becomes psi n of x, some normalization constant, which is m omega divided by pi h bar 2 to the power 2n, and then factorial n, and the whole thing under square root of 1 quarter, to the power 1 quarter, times e to the power minus half x by x naught, so this is the Gaussian factor, times the Hermite of x over x naught. So this is the solution to the time-independent Schrodinger equation. So the uncertainty principle states that delta x and delta p is greater than or equal to h bar by 2. And you can show that for the ground state psi 0, which is a Gaussian state, that this inequality is saturated. And the Gaussian is the only state for which the uncertainty relationship is saturated.